Before I start jumping into examples where we're finding horizontal and vertical asymptotes, I do want to emphasize that we are assuming on most of the examples, when you look at them, we do have polynomials that are reduced. Finding vertical asymptotes by setting the bottom equal to 0 is assuming that they are reduced, because like if you look at example x plus 1 times x minus 1 over x plus 1, for every value except for -1, that's just equal to x minus 1. You just get this nice straight line graph, y equals x minus 1, except there's technically a hole in the graph at -1. So values that make the bottom 0, but that you could cancel them out because they factor out of the top and the bottom, there you get a hole in the graph. Values that make the bottom 0, but you can't cancel, give you a vertical asymptote. Okay? Again, mostly we're looking at examples where you're getting vertical asymptotes. So here's the book's advice on graphing rational functions. And remember, we do have TI-84 calculators. We can use graphing calculators, TI-83s or 84s, or other graphing calculators. And we're definitely going to use those. But when you draw a rational function, you want to include the intercepts. You get the y-intercept by plugging in 0. You get the x-intercept by setting the function equal to 0. When you're talking about a fraction, that's 0 when the numerator is equal to 0. So we set the top equal to 0 to find the x-intercepts. Assuming it's reduced, we set the bottom equal to 0 to find the vertical asymptotes. We apply our degree rule that I mentioned to find the horizontal asymptotes. And then we'll use a calculator to help us fill it in and the asymptotes that we have, but you can also get as many mid-interval points as you want, extra points to help you draw the picture. And of course, the calculator gives you hundreds of them instantly. And then sketch a graph, finishing with all of that information. Okay. So here's an example. F of x is 2x plus 1 over x minus 3. Okay? And this one's going to wind up fitting in the standard window. Most of these rational function examples do, because the division slows down how fast they're growing, unlike our polynomials that were going off very quickly into large values. Now, it's possible we might have to zoom out, but a lot of these are going to fit in the standard window. As you see, I already have the grid there for that. So what are we going to do? We're going to find the x and y intercepts. So if we plug in 0, you get 2 times 0 plus 1 over 0 minus 3 will just give you -1/3. If you set the top equal to 0, you'll get the x-intercept. So here f of x is equal to 0 if 2x plus 1 is equal to 0 on top. And that'll give you x equals -1/2. So we have a y-intercept at -1/3, x-intercept at -1/2. Both of those pretty close to the origin there. If we set the bottom equal to 0, we'll get vertical asymptotes. So we got x minus 3 equals 0, or x equals 3. That vertical line is a vertical asymptote. And then for the horizontal asymptote, we have degree 1 over degree 1, two linear terms here. So the degrees match, so it's going to be the ratio of the leading coefficients, 2, and this is an understood 1 here, so 2 over 1. So my horizontal asymptotes at y equals a sub 1 over b sub 1 here, 2 over 1, or y equals 2. Okay. So we fill in all that information. We just have a couple of points so far. We have the y-intercept at -1/3, x-intercept at -1/2, and really important, the asymptotes. And you always want to draw your asymptotes. Computers don't, because they just plot points. Your calculator will not draw them, but you need to. Fill them in as dotted lines if they're not already on an axis. So we have a vertical asymptote at x equals 3. Draw a big dotted or dashed line there. We have a horizontal one at y equals 2. I would then just, it's accurate enough for me, if you just look at your calculator, fill it in with those points and the asymptotes and the arrows and the general behavior here. Okay, so if you look on the calculator, I do. And it's very important here, if you don't set up the fraction, use parentheses to group them. So in parentheses, we have our numerator, 2x plus 1, divided by, in parentheses, x minus 3. And there's the picture. Okay, I can fill that in pretty well here just using the asymptotes and those 2 points. If you want, you can be a lot more accurate by getting some extra points on each piece. And that would be nice, but here's, say, a pretty decent sketch. I'm looking for, you have your x and y intercepts, and you have your asymptotes correct, and then the correct, what we call the asymptotic behavior. The graph is approaching infinity as it goes toward this asymptote, and it's going toward y equals 2. And here it's going toward y equals 2 from underneath, and then toward negative infinity. Okay. So we take our asymptotes, x and y intercepts, and the picture from the calculator and try to draw a nice picture. That's my expectation of the accuracy of the graph. You can get more points and make this more accurate, and that'd be great, but be at least that accurate. Okay, another example. Quadratic over a quadratic. X squared plus 10x plus 16 divided by x squared minus 25. So we go through all of the same steps. Plug in 0, you get your y-intercept as close to -1, negative, a little bit less than -1 in the negative direction. Negative 16 over 25, so a little bit bigger between 0 and -1. Your x-intercept, set the top equal to 0. That time it's a quadratic equation. X squared plus 10x plus 16 can be factored into x plus 2 times x plus 8. Set each piece equal to 0. We have two x-intercepts, -2 and -8. Set the bottom equal to 0. We have two vertical asymptotes. X squared minus 25 is a difference of squares. X minus 5 times x plus 5. Set those equal to 0, we get plus or minus 5, or take square roots, plus or minus the square root of 25. Horizontal asymptote. This is another case where the degrees match. Degree 2 over degree 2. It's going to be the ratio of the leading coefficients. Y equals 1 over 1. Okay? So y equals 1. Fill all of that stuff in. This time we have two vertical asymptotes, one at 5 and -5. We have our y-intercept at -16 over 25, which is between 0 and -1. Then we have -2 and -8 are x-intercepts. We have our horizontal asymptote at 1 and our vertical asymptotes that I mentioned. And graph it on your calculator. And we see a picture that looks something like that. It's going to approach the two asymptotes here, going through -8. It has sort of a cubic shape in the middle, going toward the two vertical asymptotes. And I mentioned this in the earlier video. It crosses the horizontal asymptote in here, and that's fine. But on the ends of the graph, it's approaching y equals 2. And over here, it's doing that. It's approaching y equals 2 and then going toward the vertical asymptote. So fill that in. Sketch that in. Draw your asymptotes accurately. Put your x and y intercepts, and then just fill in the general shape using the asymptotes and arrows.